Okay, in this video I'm going to go through how to solve for the pH of a strong acid solution, a strong base solution, and a weak acid solution. So the first thing you need to think about is what sort of solution is it? Is it a strong acid, a strong base, or a weak acid? So you have to decide first, because how you're going to solve it depends on that. The first one is a strong acid. So hydrochloric acid is a strong acid, HCl, and so if we have a 0.1 molar solution of hydrochloric acid, it's going to completely dissociate and give 0.1 molar hydronium ion and 0.1 molar chloride ion. Okay, so in terms of the pH is the negative log of the hydrogen ions or the hydronium ions. So the hydrogen ions and the hydronium ions are referring to the same thing. So we know there that the concentration of hydrogen ions is 0.1 molar. So we do the negative log of 0.1 and gives us a pH of 1. So that's probably the simplest sort of question there in terms of the pH of a strong acid solution. We've got a 0.1 molar hydrochloric acid solution. So the concentration of hydrogen ions is 0.1 molar. Take the negative log of 0.1, gives us a pH of 1. The next example is for a strong base. So strong base like sodium hydroxide completely dissociates. So a 0.1 molar solution of sodium hydroxide completely dissociates. We get 0.1 molar sodium ions and 0.1 molar hydroxide ions. So that's these hydroxide ions here which are going to affect the pH. So there's a couple of ways we can do this. So this is just one example here. So the POH, so the pH, the P in this term here refers to negative log, and the OH here is telling us about the concentration of hydroxide ions. So the POH is the negative log of the hydroxide ions, and we've found that the concentration of hydroxide ions is 0.1. So the POH is the negative log of 0.1, gives us a POH of 1. We know that the pH plus the POH adds up to 14, so we can rearrange that and find that the pH is 14 minus the POH, so the pH in this case here is 13. So just as a way of checking that this makes sense, we've got a strong base solution, so we would expect the pH to be above 7, and we get here a pH of 13. So this is a very basic solution, so that just kind of makes sense. Okay. So then the last one then, and then the third example we'll go through is for a weak acid. So in a weak acid, it does not completely dissociate. So we have a weak acid dissolved in water, so we have the reaction here going towards the right, but this is a reversible reaction here. So the two products there, the hydronium ion and the conjugate base, will react to form the weak acid and water. So the example we're going through here is that for acetic acid. So each weak acid will have a value for Ka, and so this is the value here for acetic acid. So if we make a 0.1 molar solution of acetic acid, so take some acetic acid, dissolve it in water, make it 0.1 molar. Before it dissociates, there is very little of the hydronium ion, so just from that auto-ionization of water, but so little that we can ignore it. And there's none of the acetate ion here, so this conjugate base. So before any of this acetic acid is dissociated, there is none of the conjugate base. So that's not at equilibrium. So to get to equilibrium, it's going to have to shift to the right. Okay, so this amount here can only increase, it can't get less than 0. So it's going to have to shift to the right to get to equilibrium. So these products here are going to increase by some amount, which for now we'll just call X. The reactant here, the acetic acid, is going to decrease by X amount. Okay, so that at equilibrium, concentrations of the hydronium ion is X molar, concentration of the acetate ion is X molar, and the concentration of our weak acid, we started at 0.1, it's reduced by X amount, so it'll be 0.1 minus X. So our expression then for this weak acid, constant here, so the Ka value is equal to the concentration of the products, so the hydronium ion, the acetate ion, divided by concentration of the weak acid. So at equilibrium, concentration of the hydronium ion is X, concentration of the acetate ion is X, so X times X is X squared. Concentration of the weak acid at equilibrium, 0.1 minus X. Okay, so we can because we know the value here for Ka, so we can solve for x using a quadratic equation, but the much simpler way to do it is to ignore that 0.1 minus x. So x is going to be quite small compared to 0.1, and this just simplifies the maths on this. So the Ka value is equal to x squared over the concentration of the weak acid. So we know the value for the Ka, 1.8 by 10 to the minus 5, is equal to x squared over 0.1. So then we want to solve here for x. So x squared is our Ka value multiplied by the concentration of the weak acid, gives us that number there. We want to find x, so we take the square root of both sides. So x is then the square root of 1.8 by 10 to the minus 6, gives us this value here. So 1.34 by 10 to the minus 3. So if we look back to our table here at equilibrium, the concentration of the hydronium ion at equilibrium is x molar. And we've just found a value for x here. So this concentration of hydrogen ions or hydronium ions at equilibrium is equal to 1.34 by 10 to the minus 3. So to find the pH is the negative log of the concentration of hydrogen ions. So it's the negative log of our value here for x. So in this solution here gives us a pH of 2.87. So that there is for a weak acid, and more specifically acetic acid. So you can see that we've got a 0.1 molar of acetic acid, and it has a pH of 2.87. If we compare that to our strong acid, so the pH of this strong acid, also 0.1 molar, is 1. So the pH of a strong acid solution is going to be more acidic than the pH of a weak acid solution.